Good morning and welcome to today's lesson. Today's lesson is being drawn from the Zambian Senior Secondary Science Curriculum 5124, and also we are using the Oxford Progress in Science book, which has actually been approved as a course book for use in secondary schools as our reference material for today's lesson. So all the material that is going to be considered under today's discussion is actually material from pages 15 to page 30 under Unit 2 of Electricity. So today's lesson, being a follow-up to the previous one which we had on static charges, today we are going to deal with a sub-topic called current electricity. So now, when we look at the words current and electricity, they give us an insight into what we're going to be dealing with. When we say a current, what is a current? A current is a flow of anything, all right? When water flows in a river, we say we have a water current, all right? When wind is actually blowing, we have a wind current. In this case, we are saying electric current. The word electricity is being drawn from the word electrons. So in this case, we have a flow of electrons. So current electricity basically has to do with the flow of electrons. Now, electrons in their own sense are called charges. So in this case, we may say we are simply looking at the flow of charges. So to start this particular lesson, we'll start looking at the keywords that define the most important concepts of this lesson, and thereafter we're going to get into the nitty-gritty of this particular lesson. So we'll start by defining an electric current. So the definition: an electric current, so say an electric current is the rate of flow of charge. So the most important word here is the word charge. All right? That's our most important keyword in that particular definition. We are saying an electric current is the rate of flow of charge. The word rate at a particular point will come in as a very vital word as well, because this is another variable that we are going to consider as we do our calculations to do with electric current, or an electric current as per se. So now, let's start by looking at charge. What is charge? We know that there are two types of charges. The two types of charges are the positive charges and the negative charges. The positive charges are referred to as protons, and the negative charges are referred to as electrons. And these charges actually are measured using a particular unit. The unit of measure for charge is actually the coulomb. So we can safely say charge is denoted by the symbol letter Q, and the same charge is actually measured using a unit called the coulombs. So those are the units of measure. So we can again put that one as a highlighting point to say the unit for charge is the coulomb. Now, the coulomb actually is denoted by the symbol C, like that. Okay? Since we are still talking about charge, it's important that we remind each other of what those two charges actually do. We said the first type of charge is a positive, and we said this positive is a proton. Then the second charge is actually a negative. This negative charge is called an electron. From grade 10 work, electronic configuration, we remember that protons are actually found at the heart of an atom. They are found at the nucleus. And since they are bound to the nucleus, these protons actually do not move. They are not mobile. They can't be lost from an atom. But we see that these electrons are found orbiting around the center of the atom, which is the nucleus. And since these electrons are in a state of continuous orbit or movement, you find that these electrons, due to a number of factors, electrons can either be lost from the shells of an atom or they can be gained by a particular atom. Now, in an event where you have an atom with more electrons than protons, what is going to happen is that this particular atom is going to have a net charge of negative. If an atom has lost some electrons, what is going to happen is that this particular atom is going to have more positives than negatives, hence leaving a net charge on this particular atom of what? Positive. So when we talk about charges, we can see that charges are arising as a result of what? The difference or variation in the number of electrons in a particular atom. So now, that being the case, let us try as much as possible to dwell on the word electric current. I hope we'll be able to remember this information for now. So having said that about charge, it's important that we get back to the word electric current. What is an electric current? We are saying an electric current, which is actually denoted by the letter I. So we are saying electric current represented by the letter I. Okay? An electric current represented by the letter I is the rate of flow of charge. So now, the word rate simply means time. So this rate word is indicating time. So this particular expression here, we know that time is measured in seconds. If we say that an electric current is the rate of flow of charge, what we are simply saying is, for us to have an electric current I, we should have charges Q, which are actually flowing over a particular period of what? Time. Are we together? So now, I, being current, is equal to charge divided by time. In this case, we are saying I, which is current, is equal to charge Q over T. If we are to use the symbols so that we draw the units for I, we are simply saying I, which is current, is equal to charge is measured in coulomb. We put our Q there, our C there, divided by S. All right? So where we have I being equal to 1 coulomb per second. This unit is actually the same as 1 coulomb per second is equal to 1 ampere. Now, where does this unit come from? The physicist that actually studied electric current was called Andrea Maria Ampere. And when we are denoting the symbol for electric current, we say I is equal to A. But when we are writing it in words, we do not use a capital what? A. Because this is not a proper noun, it's someone's name. Instead, we use the letter A for the ampere. Calculate the electric current passing through a metallic conductor when a charge of 20 coulombs flows for 5 minutes. Okay, so now, when we look at this question, it's saying, calculate the electric current, so this is our I, passing through a metallic conductor when a charge, this is our Q, okay, of 20 coulombs flows for 5 minutes. Now, this 5 minutes is the time that we've been given. So we need to collect our data. before we can get into any calculation, it's important that we extract as much information as possible from the question that we have been given. So in this case, when we extract the raw information from the question, we call that information the data. So we're going to say our data there, I, which is electric current, is what we are looking for to calculate in this question. So we'll say I is equal to X. Others may express this variable, which is unknown, to be a question mark. That is not a problem at all. Then we have Q, which is equal to 20 coulombs, as highlighted there. So we'll say this is 20 coulombs. Then we have the time, T, being equal to 5 minutes. Now, one thing is for sure. When I was doing the first expression or the definitions, I said the units for time were basically the seconds. In this case, we've been given minutes, so we need to convert these minutes into seconds. That's when we can get to our equation of calculating time. Calculating the electric current. So in this case, we'll say for time T, T will be 5 minutes multiplied by 60 seconds. Okay? When we work out the mathematics, you find that 5 by 0 give us 0. 5 by 6, this is going to give us 30. So in simple terms, our time is equal to 300 seconds. Then, since our data is complete, we'll get to our equation where I, okay, is equal to Q over T. And I is equal to, our T has been given as 20 coulombs divided by 300 seconds. Okay? We can cancel our 0. Cancel our 0. Then 30 into 20. We are not using a calculator, so we'll do it manually. 30 into 20 will be 0. We'll have a point there. Into 20 will still be another 0. Into 200. If we say 30 into 200, that is going to give us 6. Okay? That will be a 6. Remainder 20. So again, another 0. So this will just be 0.066, and the figures will keep on going. So we'll say plus to indicate these figures are still going. And you put the unit, which is the amp. So that is our answer. Okay? So now, having looked at the way we can do these calculations, it's important that we now draw our attention to an electric circuit. Because we are saying these electric charges are flowing through a conductor. These conductors basically make what is called a complete path taken by the electric current. And the path is what we are calling an electric circuit. So before we draw the circuit itself, it is also important that we understand that an ideal circuit is drawn by using symbols. We do not draw a circuit using the actual electrical components that are found on a circuit board. What we use are actually the symbols of those components, electrical components found on a circuit board. So I'll simply just give a few of them here that we are going to be using from time to time. Then the others will actually talk about them as we go along. So now we have, number one, we have a battery. In certain books you find that a battery will appear like that, with a positive there and a negative there. In other books, you'll find that a battery is denoted by something that looks like this. So we have a positive terminal there and a negative terminal there. Basically, this is even a cell. It's not even a battery yet. Okay? A battery is a combination of so many cells. So this one is a cell. It's not a battery yet. This one is a cell as well. So where you have a combination of these cells, you get a battery. In this case, a battery will appear like this. So we have 1, 2, 3, 4. So in this case, what we have here is a combination of 4 cells with a positive there and, negative there and a positive that side. So this is a battery. This one is a cell, that one is a cell. Then other than that, we have another important, so I'll say this is a battery. This one is a cell. Okay? We have another one which looks like this, a very important feature in a circuit. This one is called a switch. Okay? In other books, it may be presented like that. Then Another important feature that we are going to be looking at, we have connecting wires or connecting leads or conductors. So this is just a single connecting lead. Then we may have something like this. This is a connecting lead that is making a T-junction. So we can call these as metallic conductors. Then we have another important feature that we are going to be seeing with a capital letter A inside. This one is called an ammeter. Going to look at its use later on. We have another one. This one is called a voltmeter. Then we have this one that looks like this. This one is a bulb. Okay? So amongst a few that we're going to deal with, we have these plus a few more that are going to fall, that are going to come into perspective as the right time comes. Like for example, we have resistors, rheostats, and so many other things. So our circuit will look like this. So that one will be connected to the bulb, and that side we're going to have our switch. Okay, so that being the case, we have this battery which is negative there, and then we have a positive that side. Okay, then we have our bulb which is actually not on as at that point because our circuit is not complete. Remember we said an electric current is seen passing through a complete path. Now this path is not complete because our switch is actually open. The moment we close this switch, what is going to happen is we are going to have a flow of charges. Now, where are the charges coming from? The charges are coming from the power source. This is the powerhouse or the engine of this particular circuit. Whatever is happening in this circuit is coming from the battery. So what we are seeing here is this part being positive. We are going to see a flow of current in that particular direction. Okay, so this current will start off its journey from the positive terminal, pass through the switch, get to the bulb, and we are going to see the bulb light up. Then, if you remember very well, from our definition we said an electric current is the flow of charge, and we said these charges are basically electrons. And we know that electrons cannot be found at the positive terminal. These electrons are found at the negative terminal. So the normal way for electrons to flow is that they are going to flow from the negative terminal going towards the positive terminal because they have an affinity for a positive end. So you see these electrons moving from the negative terminal going to the positive end. Now, what is this confusion that has been created here? This confusion here can actually be sorted out by means of saying the flow of charge from the negative to the positive is simply the flow of electrons. So electrons will always flow from the negative terminal going to the positive terminal. But what is this that is flowing from the positive going to the negative? What flows from the positive to the negative is what we are calling conventional current. So this is conventional current. So we see a conventional current moving from the positive terminal, passing through the switch, and of course through the bulb going to the negative. But for electrons, we'll see electrons actually flowing from the negative going to the positive terminal as it were. And because of that, what we consider as being ideal current in our syllabus is the conventional current. So much of what we are going to be dealing with or talking about is this conventional current that has come into play. Now, if we are to calculate this current in our circuit, there are devices or appliances or electrical components that help us to measure the current that is passing through this particular circuit without us actually getting to know the value of the battery or the resistance being offered by the bulb. What is that instrument? Remember, I talked about an instrument called an ammeter. All right? The word ammeter is coming almost similar or close to the word ampere. The word ammeter is, or rather the instrument, the ampere, is used to measure an electric current passing through a metallic conductor. And in most cases, you find that we place this ammeter before we have an electrical component. So before this bulb, we are going to introduce our ammeter. All right? And when you look at an ammeter, the diagram of an ammeter from the book, you discover that the ammeter has two sides. It has one side where the terminal is red, and there's another side where the terminal is black. The red terminal is connected on the positive end. So the red terminal is connected on this line coming towards the ammeter, or into the ammeter. Then the black line, which is actually the negative terminal, is connected on the on the negative end, the one that goes to the negative, the line that goes to the negative. So we'll connect our ammeter there. Now, when we connect our ammeter there and switch on our circuit, you'll find that it's going to give us a reading. And these ammeters come in different sizes, in the sense that they have different values that they are able to actually measure, the values of current they're able to measure. So you find that if we are dealing with smaller values of current, like the one we had earlier on, which was 0.066, like that amps, you find that the type of ammeter you need there is called a full scale deflection, 1 FSD ammeter. Now, if the values are ranging between 1 to about 5, you need to use what is called a 5 full scale deflection, okay? 5 FSD. It's actually FSD. Okay? So the word FSD that you see on the ammeter there is called full scale deflection. So the maximum deflection it will give will be 1 for this one. This one, the maximum deflection is actually 5. Okay? So now, if we knew the value of the power source and we knew the resistance there, we can actually play around this figure and that figure to still get the ammeter reading, which is something we're going to consider later after we've looked at resistance. Okay, so as a follow-up to the lesson that we had on conventional current as well as the flow of electrons, we're going to do a virtual lab just to explain what was happening, and so that you can easily see and differentiate the way conventional current flows as well as the flow of electrons. Now, to do this, we are going to do a complete lab. I'm going to use the components or electrical components that are used in the lab on a circuit board. So to start with, I'm going to get our power source. In this case, it's actually a battery, and when you look at this battery, it has a positive terminal there and a negative terminal on that side. Then we're going to connect a connecting wire or a connecting lead connected there. Then I'll connect another wire, that particular point. Then I'll connect, like we had said, a switch. So that's our switch there. Then I'll connect our ammeter. It looks very different from the one that we have in the book, but it's the same instrument. No need to worry. Then I'll connecting lead there. And I'll connect our bulb. And connect another connecting lead. Our connecting leads cannot actually make a turn, so I'll be using independent connecting leads. Though it will be difficult for you to actually see that I've used so many wires to just appear as one. Get the last one, attach it there, and extend it to that corner there. So there we are. We have our circuit. So since the switch is open, you see that the ammeter is reading 00 there. But the moment I close this particular switch, you're going to see that the ammeter is going to give us some reading. So let me try connecting this one. When I close it, there we are. You'll see that it's giving us a reading of 0.90 amps. All right. And then one important thing is that we are seeing the flow of electrons from the negative terminal. They are flowing like that, going towards the positive terminal. In this case, we are just considering the movement of electrons. So you see electrons moving slowly from the negative going to the positive. But if I'm in need of conventional current, I'll change it there. What we'll start seeing now is conventional current coming from the positive terminal. So it's coming from the positive terminal marked in red and going that way. And it's going up. Okay? So now, I'll do one simple thing to emphasize the concept of electrons. So the number of electrons flowing, or the rate at which these electrons are flowing, is dependent on the strength of the power source that we have. For example, if I open up this part of a circuit and introduce another battery, you see that the speed of the electrons has actually increased, and also the brightness of the bulb has actually increased. All right. In the same vein, if I'm to take it to conventional current, you see that the rate at which the arrows of conventional current are moving has actually increased. Also, the reading of the ammeter there has increased from 0.90, which we initially had, to 1.80 as the reading for current. So the value or the rate at which current is flowing is dependent on the amount of energy being supplied by the battery or the cells. Where the cells are supplying more energy, we'll see that the rate of flow of these electrons is going to be increased, or the rate of flow of conventional current is actually going to increase. So this actually is just a presentation to help us understand what we were talking about on the board. Well, for today, I guess our lesson will end here. The next time we meet, we are going to look at two important variables that come with the power source as well as the power consuming component. So we're going to look at, for this one, we are going to look at what is called EMF, the electromotive force. And under this one, we are going to look at what is called the PD, or the potential difference. For today, we'll end here and go and read as much as you can on the two items that are going to be considered in the next lesson. Thank you very much.